Hello, everybody. My name is Andrii Mironchenko. Welcome to my talk on robust forward completeness, a bridge between well-posedness and stability. Here, we will discuss the global existence for solutions of certain distributed parameter systems. At the same time, first, let me summarize what do we know about ordinary differential equations. Therefore, for several first slides, we will consider the classical nonlinear ODE systems. Here, the state is X, and it is in Rn, and the inputs are denoted by U, and they belong to the class of L infinity. The nonlinearity F is continuous in both variables jointly, and also F is Lipschitz continuous on bounded subsets, as defined here. So for any ball of radius R, there is some constant, Lipschitz constant L of R, such that this inequality holds for all x, y from these balls and for all v of magnitude not exceeding R. Also, we fix R large, and we fix the set D, which are all inputs with a magnitude not larger than R. And we will call this the set of admissible inputs. Now, what do we know about the existence uniqueness of solutions? Well, according to the classical Kara-Teodori theory, we know that for any initial condition and any input U, there is a unique maximal solution of this system, and we denote it using the flow notation in this way. Also, we know that if this solution is not defined globally on the whole R plus, then it exhibits blow up in finite time. But we're actually interested in global solutions. Therefore, we need some more definitions. We will call this system forward complete if all the solutions are global, so exist on R plus. Also, we will say that this system is robustly forward complete if it is forward complete, and in addition, for any radius R and for any time tau, the trajectories starting in the ball of radius R, subject to inputs from our admissible set D, all these trajectories are uniformly bounded on time interval 0 tau. So we have uniform bound for all trajectories. Now let us look at these two definitions. The forward completeness tells us only about the global existence and nothing more. It does not tell us anything about the bounds of possible solutions. And robust forward completeness, in contrast to that, already gives us the bounds for solutions or for some sets of solutions on finite time intervals. It is worth to compare it with the stability notions. And let us take the concept of a Lagrange stability. We say that this system is Lagrange stable if it is forward complete, and at the same time, for any radius R, the solutions starting in the ball of radius R, subject to all inputs, are all uniformly bounded globally in time. So the difference between these two concepts is that here in Lagrange stability, we require the uniform bounds for all times, and here only on a finite time interval. And here we see the difference. So forward completeness tells only about existence and with no bounds at all. And stability notions give us the bounds which are, well, stability theory is about notions where we need to have global in time bounds. And this is something in between, because it already gives us some bounds, but only on finite time intervals. Therefore, we can see that robust forward completeness is a bridge between well-posedness theory and stability theory. And now we come to the first important result here, which is due to Ling, Sonntag, and Wang, 1996. Assume that F satisfies all our standing assumptions. So we have continuity in both variables plus Lipschitz continuity in X. Then forward completeness is equivalent to robust forward completeness. It's very important because if we have just forward completeness, what we can assume, then we automatically have also bounds for these finite time reachability sets, which gives us a lot more in our hands. Okay. It's important that here F should satisfy these assumptions. So it is not that for any forward complete system, we automatically obtain robust forward completeness. No. So here we really exploit the regularity of F. Okay, but actually we have much more. So then also in another paper by Andrii and Sonntag in 1999, also it was shown that forward completeness, and thus robust forward completeness, are equivalent to existence of a smooth function V, which is proper or coercive. So this means that we have this uniform bound from below in terms of k infinity functions. So these are functions which are 0 and 0 continuous and increasing. And also this function V should increase at most exponentially along the trajectories. So here we have just Dini derivative or Lie derivative of V. So one more time, forward completeness is equivalent to existence of a smooth Lyapunov-like function V, which has uniform bound from below and which increases at most exponentially along the trajectory. Let me add one more criterion, that forward completeness is equivalent to existence of a Lipschitz continuous function V, which is proper and which again increases at most exponentially, but also with this drift term. So clearly this result is stronger, so this than that one, right? But at the same time, if we would like to show robust forward completeness, then it is enough to have just such a Lyapunov function. Okay. Now this result helps us to prove many other important results. Here, let me show just a very simple application of that. So if F satisfies our standing assumptions, and if F is in addition linearly bounded, then the system is robustly forward complete. I mean, it's a well-known result. Usually it is shown by application of Gronwall-Bellman lemma, but here we get it indeed in one line. We just take V as x squared, we differentiate it along the trajectory, we obtain such estimates, and in the end of the day, we see that V dot is less or equal than this expression, which by previous result automatically implies robust forward completeness. This is clearly just a toy application. In reality, robust forward completeness is helpful for much more involved results. Namely, Lin, Sonntag, and Wang have used this for derivation of converse Lyapunov theorems for global asymptotic stability. In this paper by Fabian Wirth and me, we have developed non-coercive Lyapunov functions theory, where robust forward completeness has played an important role. Also, it is important for getting criteria for uniform global asymptotic stability for infinite dimensional systems. Finally, related properties such as boundedness of reachability sets is essential in characterizing input to state stability for infinite dimensional systems. Also, as I have told, for non-coercive ISS, Lyapunov theory plays an important role. And finally, it was crucial for characterization of global asymptotic stability for time delay systems, as shown in this paper. Okay, so this is our take-out message one. So what we know about global existence for ordinary differential equations. So forward completeness is equivalent to existence of such Lyapunov functions. Now, what we would like to do in the rest of this talk is to analyze what we can show for infinite dimensional systems. And first of all, let me tell how these smooth Lyapunov functions have been obtained. So in these converse Lyapunov results, usually one gets first Lipschitz continuous Lyapunov function, and afterwards one uses so-called modification technique to make a Lyapunov function smooth. Let's say to construct another Lyapunov function which is close enough but at the same time smooth. However, this modification technique, which is available in Rn, I don't know any general results in Banach spaces. So there are for some specific other types of Banach spaces, but these are just examples. So general technique for me is not known. If you know, I would be happy to know. Just leave it in comments. So therefore, if we would like to generalize this result to infinite dimensions, then this criterion we will not have. But we can still hope for this one. Also, the second, what I would like to say is that in infinite dimensions, we have no more equivalence between forward completeness and robust forward completeness. Even more. If we take this example from the paper, my paper with Fabian Wirth several years ago, then we will see that for forward completeness, even together with global asymptotic stability, does not imply robust forward completeness. Let me present this example now. As a state space, we choose the Hilbert space L2, which are infinite sequences with a bounded, which is square summable. And each component of this sequence will be a two-dimensional vector. And now on this space, we consider the following system. We just take such a planar system and take infinitely many copies of that. Let us analyze this system. The second dynamics of yi is trivial, just exponential decay. The dynamics for xi, well, locally it's also decays exponentially because close to zero, the linear term dominates. But for large xi and yi, this term will dominate and it will lead to blow up of trajectories. Well, that's not what we would like to have. So I would like to have a forward complete system, which is not robustly forward complete. To make such system forward complete, we add a damping. And here it is. So then we add cubic damping. So then if we take small xiyi, with this guy still dominates, these linear terms. So locally close to the equilibrium, we have the exponential decay. For state, if it is larger, then this quadratic term may dominate, and therefore it tries to make the system blowing up. But when xi begins to be large enough, then cubic term starts to dominate and it flattens out the trajectory. So we will not have blow up, but it will then decay. Why it will decay? Because yi tends to 0. And hence this coefficient goes to 0. Then this term will vanish after long enough time, and linear term and cubic term will lead the system to 0. So what we have for any particular such mode, that corresponding trajectory will tend to 0. Now let us analyze the whole system. To have local exponential stability, we just can take this Lyapunov function and we easily get it. It's not that hard to see. What is more interesting is to prove forward completeness and global asymptotic stability. Then we just see that our state space is L2, and this means that for any initial condition and for any epsilon, we can find such number n so that the tail of the corresponding sequence Z will have L2 norm less than epsilon. Okay? What does this mean? This means that the tail will here have small norm. This means that the exponential dynamics will dominate this stabilizing dynamics for all these modes. And hence, all of them will be stabilized by linear dynamics. And the only nasty terms will be first terms finitely many from 1 to n. But here we have already analyzed each particular mode will decay to 0 when time goes to infinity, and hence, since we have finitely many, then we can find uniform time so that all these modes tend to 0 when time goes to infinity. And overall, this means that for any initial condition, the corresponding trajectory of the whole system is well-defined and tends to 0 when time goes to infinity. And so we have forward completeness and global asymptotic stability. At the same time, we do not have robust forward completeness. Why don't we have it? We don't have because here our damping depends on I, and the larger will be the mode, the smaller will be the damping. And so taking the same initial conditions for larger and larger modes, we will have that blowing up term will lead us higher and higher within some given finite time. And this will mean that we do not have robust forward completeness. Hence, in finite time, from the initial conditions with the same norm, we can go arbitrarily far away from the origin. So, this means that forward completeness is essentially weaker than robust forward completeness. And just note also that in the previous system, the nonlinearity was Lipschitz continuous. So, from this nice picture, which we had for ordinary differential equations, the only hope which for infinite dimensions can be here. We could try that robust forward completeness is equivalent to existence of a such Lyapunov function. And well, one direction is not hard. So if we have such a Lyapunov function, then we will definitely obtain robust forward completeness, and it's a routine. So the interesting is the converse implication, and I would like to explain it next. But before that, let me explain what we will understand under infinite dimensional systems. So under infinite dimensional systems, we will understand the triple consisting of the state space X, input space U, and a flow map phi. And we call it a control system if for any initial condition and any input U, the corresponding value will be well defined on a some non-empty time interval. And yeah, so here Tm is the maximal existence time. We also assume that the trajectories are continuous, and we assume also that co-cycle property holds on the whole domain of definition. There are also several further axioms which are needed, but I don't want to tell all of that. I just tell that ordinary differential equations, many classes of PDEs with Lipschitz nonlinearities, broad classes of boundary control systems and time delay systems are within this general framework. So it's general enough. Okay, also we, as for ODEs, we take some number R, which can be finite but also infinite, and we consider the state of the admissible inputs, which is just a ball of radius R in U. Well, and if R is infinity, then this will be the whole space U. Now we will need one more assumption on this set D. We assume that if we take any two inputs from this set D, and if we concatenate them to each other, then the corresponding resulting input will still be in the same set D. Let me give some examples. If U is L infinity, then we definitely can take two L infinity functions, glue them together, and we again obtain L infinity function, which also has a norm not larger than norm of these two ones, of the maximum of them. And therefore, the assumption will hold. If we take piecewise continuous inputs, then the same holds. If we take LP inputs and R is infinity, so D equals to U, then the above assumption also holds. We can take two LP functions, glue them together, it will be again an LP function. The norm may increase, but at the same time, it will stay in LP. Therefore, assumption will hold. But if we take R less than infinity, then assumption will not hold, because we can take two LP functions, glue them together. If the resulting norm of the concatenation may be larger than the norm of the two original ones, and we may go out from this set D. We will stay in U, but we will be out of D, and this is not what we want. So in this case, the assumption will not hold. Okay, it will be important for the next proofs. Okay, now we define several properties which I have already defined for ODEs, but now I will just repeat it for this abstract class of systems. We say that sigma satisfies boundedness implies continuation property if for any initial condition and any input, such that the solution exists only on a finite time interval, this solution blows up within this time Tm. We will say that the system is robustly forward complete if it is forward complete, so all the solutions exist globally, and at the same time, for any r, for any radius r, for any time tau, the corresponding finite time reachability sets of our system are bounded. Well, so this means that all the trajectories starting in the ball of radius r, subject to inputs from admissible set D, will be uniformly bounded with a uniform bound on the for times from 0 to tau. Finally, the flow of our system sigma, we call it Lipschitz continuance on compact intervals, if for any time tau, for any radius r, there is a Lipschitz constant such that we have such an inequality for all xu from ball of radius r and for all admissible inputs. That's what we have. And now we can formulate our main result, which is in this, which is currently submitted. So we take any our abstract control system which satisfies the big property. We assume that the corresponding flow is Lipschitz continuance in compact intervals. Then robust forward completeness is equivalent to this property, to the fact that there is psi of class K infinity, such that the norm of the trajectory is upper bounded by these guys. So it's not a big deal to show this implication. I mean, clearly this implies robust forward completeness. So, but the converse is a bit harder, but just a technical stuff. So why it is important, this restatement? Because a robust forward completeness is a qualitative notion. So we just say, if we start in a bounded ball, if we apply inputs from our set D, then we will have uniformly bounded trajectories on finite time intervals. But it doesn't tell what will be this bound, how it depends on the norm of the state, how it depends on time. This information is not given in robust forward completeness. And here we have this information. We have not only the finiteness of the bound, but we also know how it depends on the norm of X and on time. And this will be important in the sequel. So you may see that this is just a better definition of robust forward completeness, which is more useful in practice. More constructive definition, if you like. What is more interesting is that robust forward completeness is also equivalent to existence of a Lipschitz continuance map, which satisfies these sandwich estimates and such that Lyapunov function, well, this map V, increases at most exponentially along the trajectories. The only difference to the ODE result, which I have presented earlier, is that here we require that for V, this is some bound from above holds. Not, however, that for ODEs, this is always satisfied, because V is a continuous function. If we maximize it on a bounded set, then we always will have such a bound. So it was, let's say, implicitly there, although I haven't written that. But here it will be not implicitly there, and we need to require this property. Okay, well, first of all, I mean, if we have such a Lipschitz continuance map, it is easy to see that the system will be robustly forward complete. So it's not hard to see again. And the only hard implication here in this theorem is from this second property to the third one. And that's what I would like to present in more detail. So we have robust forward completeness in this more handy version. And now what we do, well, usually if we want to prove some converse Lyapunov results, then we construct Lyapunov functions as integrals or suprema of the flow map with some scaling coefficients. Here we do similar things. We take Lyapunov function, well, let's say pre-Lyapunov functions Vk in this form, and we specifically choose these scaling coefficients. Namely, this rho is less or equal than xi inverse, where xi comes precisely from this definition. And well, that's why we needed this kind of restatement, because now we can use this psi here for construction of Lyapunov function. So rho has this form, and also we can always choose it globally Lipschitz with the unit Lipschitz constant. And this gk is a function of this form. So like identity minus 1 over k, as long as this is positive. Okay. And now what I would like to explain is why we need all these terms. And now we will see it. So first of all, what we would like to have is some sandwich bounds for Vk. Okay. Sandwich bound from below is easy to obtain, because here we take it, so it equals to supremum over all u and all t of this expression, and we can just plug in t equals 0, and we will have a bound from below. If t is 0, this guy is identity, and here will be just norm of x, and then we have precisely this bound. So not a big deal at all. To have upper bound, we take the supremum over all u and all t, and now we use that rho is less or equal than psi minus 1. So we estimate rho by this psi minus 1. And now we use that norm of the trajectory is upper bounded by this thing, by robust forward completeness. And so we have such an estimate. And now you see, why did we need this rho? We need it because now this psi minus 1 applied to this guy will neutralize these terms. And we will have that this is less or equal than this expression. And now why we don't needed this exponential here? Well, because it will also neutralize, let's say, this t, and this will make all this supremum finite. And actually, we can upper estimate in this way for some constant c. So the bound from above is very good, is what we need actually. The bound from below is not that good. Why? Well, because gk is given by this expression, and it equals to 0 when r is less than 1 over k. So taking x small enough, we will have that rho of this guy is small enough, and then gk of this guy will be just 0. So here we have in general for small x just greater or equal 0. And it's not what we have. Okay, let's go next. Why did we need all this gk, you may ask? And the idea why is that now one can show, after some computations, that actually this supremum was taken over all times positive, but it was always attained on a finite time interval, which depends on the radius of the ball where we take initial condition and on k. On this parameter. Okay. This is the importance of this guy gk. And why do we need this finite interval? Well, we need because we know that this flow is Lipschitz continuous on finite intervals. And now, using global Lipschitz continuity of this guy, global Lipschitz continuity of this guy, and Lipschitz continuity of the flow, we can obtain that also this vk will be Lipschitz continuance on bounded balls, which is what we need. We need some regularity for these functions vk. And also one can show that vk satisfies such a growth condition. And now, having all such functions vk, we can define what will be our RFC Lyapunov function. So the function which we would like to construct. And it will be a series over vk scaled by these coefficients where m is this Lipschitz constant. One can show that now this function will satisfy all the needed properties. In particular, since we take here k from 1 to infinity, then we will have here terms which are non-zero for smaller and smaller x. And in this way, we can obtain also nice bound from below, which we did not have for vk. Okay, so if we fill all the technical details which should be added, then we will obtain now the full proof of this result. Just some comments. We can compare this proof with this result to the original proof by Andrii and Zonta, who have proved the corresponding result for ODE systems. Well, one of the things is that Andrii and Zonta use in their proof the existence and uniqueness of backward solutions. Well, clearly, if we are in ODE setting, we assume that F is Lipschitz continuous, then we have not only existence uniqueness in positive direction, but also in negative direction. And Andrii and Zonta use it in their proof. Here, for our abstract systems, and also for many particular types of systems, we do not have backwards existence. We may have existence in forward time, but nothing in the backward time. Therefore, here we use a completely different proof technique. Although the result looks very similar, but actually the technique behind it is really different. Also, as I have told, Andrii and Zonta obtain a smooth Lyapunov function using modification technique. So they first derive the Lipschitz continuous Lyapunov function and then do additional arguments to prove that it can be made smooth. Here in the Banach spaces, I don't know such general technique, and therefore we just stay with these Lipschitz continuous functions, and that's what we can obtain. At the same time, for most applications, it is enough to have such a function. Okay, now you may ask how we can verify the axioms, well, the assumptions which we need, because what we wanted a control system which has big property, and also whose flow is Lipschitz continuous with on compact time intervals. How we can verify it? Well, to give an example, we can consider a special case of infinite dimensional systems. X dot equals AX plus f of XU, where A generates a strongly continuous semigroup over a Banach space X, and F is continuous jointly in both arguments, and Lipschitz continuous on bounded subsets with respect to the first argument. Our inputs are piecewise continuous functions now. And also we here fix some bounded R greater than 0 and consider this space of inputs. And now, similarly to the ODE case, we have that for each initial condition and each input, there is a maximal solution of this evolution equation, where solution we understand in the mild sense. And also one can show that the big property holds, and furthermore, if we have robust forward completeness of this system, then also the flow will be Lipschitz continuous on compact intervals. And now we can give the following corollary of our main result. If we consider this kind of systems satisfying the assumptions I stated on the previous slide, then robust forward completeness is equivalent to existence of a Lipschitz continuous map satisfying these properties, precisely those which we had in our main result. The difference that here we do not require Lipschitz continuity of the flow, but we obtain it as a consequence of this result. Okay. Now, finally, I would like to tell some words about a related property, about so-called boundedness of reachability sets. So robust forward completeness was forward completeness plus the bounds for trajectories where the inputs were taken from a fixed in advance set D. Boundedness of reachability sets is forward completeness plus boundedness of all such sets of trajectories where we take the inputs all of radius r. And r can be arbitrary here. We claim that this is finite for all r. Okay, so here we fix it once and we stay just with that set, and here we increase the ball in which initial conditions are taken, and in parallel we increase the ball from which we take the inputs. So this makes these properties different from each other, although clearly closely related. Let us see it on examples. If we take the set D as the full space of inputs U, then BRS is clearly weaker than robust forward completeness, because here we take supremum over all inputs, and here we always take supremum over bounded balls for each R. For example, if we take this scalar system, then clearly it has bounded reachability sets. If we take uniformly bounded inputs, we get uniformly bounded trajectories on finite time intervals. But this system is not robustly forward complete, because if we start with any non-zero point, then applying larger and larger inputs, we can increase arbitrarily fast, deviate from the origin. Okay, therefore it is not robustly forward complete. At the same time, if D is not the whole space U, but if D is just a ball of radius R for finite R, then already boundedness of reachability sets is stronger than RFC, because we can take such a system. If we specialize it only for inputs of norm less or equal 1, then clearly it will be globally asymptotically stable, and therefore it is robust forward complete. At the same time, if we do not specialize for such inputs, but consider just general inputs, and then clearly it does not have bounded reachability sets, because taking U identically 3, we will have blow up in finite time. We have no forward completeness even. Okay, therefore these two properties are really different from each other, though closely related. And now what we have next, it is natural to try to prove similar characterizations for Lyapunov characterizations for boundedness of reachability sets. At the same time, I don't know how to do it. And I don't know such results even for ODE systems. What we can show is that if we have an abstract system satisfying big property, then if we have a Lyapunov-like function, which satisfies the sandwich bounds, precisely the same as before, and such that we have exponential increase for x large enough. If such a Lyapunov function exists, then we have boundedness of reachability sets. At the same time, we have no converse result. And that would be an important open problem, because boundedness of reachability sets is important if we would like to use the criteria for ISS, the ISS superposition theorems, or if we would like to employ non-coercive ISS Lyapunov theory. And now we come to conclusions. So first, for infinite dimensional systems, forward completeness is essentially weaker than robust forward completeness. At the same time, we still can characterize robust forward completeness by existence of Lyapunov-like functions with at most exponential growth. We have here new proof strategy in compared to the original paper where forward completeness was characterized for ODE systems. And you can find the detailed proof in this paper by myself, which is currently submitted to SCL, but which can be already found on arXiv. Well, finally, here you can see also some references to the papers where the results, important results, were published, which exploit robust forward completeness or boundedness of reachability sets. So here, Lin, Zontag, and Wang have proved smooth converse Lyapunov theorem for uniform global asymptotic stability, which exploited equivalence between forward completeness and robust forward completeness. In this paper by Fabian Wirth and me, we have developed the non-coercive Lyapunov functions for dynamical systems, and we derived criteria for uniform global asymptotic stability, where RFC plays an important role. Using BRS property, we can characterize input-to-state stability and develop non-coercive ISS Lyapunov theory. And finally, in this paper, it was shown that question whether forward completeness is equivalent to robust forward completeness is important to understand whether global asymptotic stability is equivalent to uniform global asymptotic stability. So at this point, I would like to thank you a lot for your attention and looking forward to your questions.